And Smart Grid lecture series. In this video, we are going to discuss about major protection issues of standalone microgrid. So, when a microgrid operates in standalone mode, the protection consideration becomes significantly different from those for the grid connected condition. Actually, this section discusses four main protection considerations. Assuming a proper separation of microgrid at point of common coupling, which are listed as distribution system fault protection. Second one is protection of micro sources. Third one is National Electric Code requirement for distribution transformer protection. And fourth one is the neutral grounding requirements. And basically the protection requirement which provide a basis of a design criteria of a distribution protection system, which will consist of a 3S, that is sensitivity, selectivity and speed. Sensitivity is a protection system should be able to identify an abnormal condition that exceeds a normal threshold value. So that should be sensitive. Then selectivity, protection system should disconnect only in the faulted part of the system in order to minimize the fault consequences. Then speed is means the protective relay should respond to abnormal condition in the least possible time in order to avoid damage to the equipment and maintain the stability. Regarding the microgrid distribution system protection, there are few points we need to discuss. The first one is the microgrid medium voltage system protection. The fault occurring in medium voltage zone, that is near to the utility, it can be easily cleared just by tripping all the micro sources. However, before developing any protection scheme for medium voltage zone, the probable impact of medium volt faults on the microgrid operation must carefully studied. And assuming that the microgrid to be a typical on-site active low voltage distribution system, the only medium voltage protective devices it would include are the distribution transformer fuses on the medium voltage or a low voltage transformer connecting it to the utility. The only protective device will be a distribution transformer fuses that is connected to the utility. And for an medium voltage side fault during grid connected operation, these fuses are typically set to operate very fastly within a time range of 0.1 to 0.2 second for the available fault current from the utility grid. Actually, normally 20 to 50 times the maximum load current carried by the fuses. On other hand, for a low voltage side fault resulting in for a low voltage side faults which will be reflected a fault current 10 to 20 times the maximum load current of the fuses. They are actually set for a time delayed operation within the 0.5 to 1.5 seconds. Actually, the problem of protection system of a standalone microgrid is that the drastic reduction in the fault level. A medium voltage fault of a similar magnitude in a standalone microgrid would result in fault current only about 5 times the full load current of the system. So this is actually much lesser compared to 20 to 50 times of times greater fault current in grid connected condition. So in a grid connected condition, the fault current level is very high, and in a standalone condition, it will be very low level. So thus, with extremely inverse time characteristics, the distribution transformer fuses will be extremely slower to operate for such a fault, and it would be very difficult to coordinate them with the microsource protection. So we cannot think about a protective system that is very suitable to grid connected operation will be suitable in a standalone operation. So that is the main thing. So under this conditions, there are only two choices we have. First one is to accept that a medium voltage fault within a microgrid would lead to a total microgrid outage. Or second is to install additional protective devices to the medium voltage system that is properly coordinated with the microsource protection systems under standalone condition. So either we need to install an additional protective device which will be protect the microsource during its standalone condition also. The first or otherwise first choice is we can use a fault level same as that of a grid connected mode. That means whenever a grid is under faulty condition, means the microgrid also will be completely in the outage. We cannot utilize the microgrid. So in that way, it is not efficient. So second one is we can design a separate protective system for microgrid in order to protect the microsource under the standalone condition. The first choice of accepting misoperation of a secondary contingency is definitely more economic and tolerable, as the loss of distribution transformer does not lead to any extra loss of generation for the standalone microgrid. So whereas the second choice involves the expense of adding extra breakers and relays in the medium voltage side. The second consideration in a microgrid protection in the medium voltage line is that low voltage fault clearing requirements. So conventional protective devices actually operate for a maximum fault current levels of about 2 to 20 times the maximum load current. They are usually time current coordinated with one another so that the device very closest to the fault operate first. So these devices are actually known as the primary devices, while the devices away from the fault are known as the backup devices. So during any fault, the backup devices are adjusted to operate slower than the primary devices at the maximum fault current that flows through the both of them, even though both detect the fault. Then and the falling of fault current depends upon the impedance of the lines or transformers between the generation point and the fault point. For a medium voltage and low voltage distribution network, the inverse time overcurrent and high set instantaneous overcurrent relays are used. This actually makes the fault clearing times more or less proportional to the distance of the fault from the substation. And the generation point is termed infinite bus in fault studies, but in microgrid is not appears as infinite bus on the medium voltage side of the transformer. and a transition of a microgrid from grid connected to standalone mode may slow down the fault clearing and limiting the backup protection. And this will be depends upon the number of situations. First one is whether the time dependence characteristics of the micro sources exhibit subtransient, transient, or synchronous time effects. Then second one is the value of pickup setting of high set instantaneous overcurrent relay with respect to the maximum fault current available from the microgrid. And third point is how much inverse the time current characteristics of the relays is in the region of fault current provided by the microgrid. That is how much the operating time changes for a changes in the fault current. Then third consideration is the presence of dispersed DERs or distributed energy resources in the microgrid. That is the impact of having dispersed renewable energy based resources on the microgrid protection system must be compared with that of having a central microgrid generation facility. Dispersed means it is distributed energy resources in a microgrid. So these must be taken into account while designing a reliable and a secure protection systems. That is, if you have in your microgrid have lot of dispersed generations, and these should taken into account while designing the protective system. And the protection of micro sources. So design of a reliable micro source protection scheme should consider the following issues. And extensive dynamic simulation studies should be carried out in order to address these issues. The issues are deciding the acceptable voltage and frequency protection tolerance for a standalone microgrid. Then second one is assessing whether there is any need for anti-islanding protection for DERs or distribution energy resources, and if such a protection exists, how it may be disabled or overridden while the microgrid is operating in the standalone mode. Then third one is examining whether the existing anti-islanding technique may leads to voltage or frequency instability if used in a standalone microgrid. And fourth one is assessing the needs for an under frequency load shedding scheme for microgrids on reliability and coordinating it with the same scheme of the utility. The anti-islanding means it is a condition at which the microgrid is disconnecting from the main grid due to some fault or disturbances, and it is continued to be in operating mode. That is anti-islanding. That is the normally a microgrid will be connected to the grid. So whenever islanding occurs, that is islanding means that the grid in the grid there will be if there is any contingency or fault or disturbance occurs, the grid will be disconnected, or that is microgrid and microgrid will be disconnected from the main grid, but the microgrid will be restore its operation as a standalone mode. Then it is known as the anti-islanding process. So that should be these are the main points regarding the protection of micro sources. And islanding means, so islanding is the situation in which the distribution system becomes electrically isolated from the remainder of the power system and yet continue to be energized by DG connected to it. That is what is islanding. That is the situation in which the distribution system becomes electrically isolated from the reminder of the power system, but yet it is energized by DG only. That is the islanding process. That is the main grid part is main distribution system. Utility part is disconnected from the main grid, but still the grid is energized with grid is energized with the power or micro sources from the DG. And anti-islanding is nothing but we are disconnecting islanding the microgrid is disconnecting from the main grid after a fault occurs, and the microgrid is continue to be operate in a standalone mode. That is anti-islanding. So the traditionally a distribution system doesn't have any active power generating source in it, and it doesn't get power in case of a fault in a transmission line upstream. But with the DG present in it, the this presumption is no longer valid. So if there is no such kind of distributed generation is connected to the grid, there is no concept of islanding, and still the DG is feeding to the utility grid. So issues with islanding also should consider while we are designing the protective system. There are the possibility like line worker safety can be threatened by DG sources feeding a system after primary sources have been opened or tagged out. That means whenever a fault occurs in a grid, the distribution line is faulty, but still that line is energized because of the presence of distributed energy resources or microgrid. So that will affect the safety of a line worker. They may not be aware about that power from the distributed energy resources, and they will continue to work in any maintenance work, and that will be affect the safety of the line worker. And the voltage and frequency may not be maintained within the standard permission level, and the instantaneous reclosing could result in out of phase reclosing of DG. These are some of the issues with the islanding in the main grid.